So welcome back to STEM Baba. We were discussing the chapter rotational dynamics and static equilibrium. As of now, we have discussed three topics: torque, relation between torque and angular acceleration. Also, we discussed zero torque and static equilibrium. And today in this video, we'll start with a fresh topic: center of mass and balance. So let's start the video. So center of mass and balance. So consider that you are constructing a mobile. So you took a thin rod and you make a knot by using thread at a distance x1 from this mass m1, and this rod is suspended here, right, from this point. Now this rod is suspended at this point. Now our task is to tell that what should be the mass m2 so that the system is in equilibrium. Now in the previous video we saw that whenever the system is in equilibrium, the net torque should be equals to 0. So if you take this point to be your axis of rotation, then I can say that the net torque about this point should be equals to 0. Now if you consider this gravity force m1g, here the gravity force would be m2g. Now this would create a counterclockwise moment, so counterclockwise torque basically. So this should be m1g into x1, and then this will create a clockwise torque, so minus m2g into x2. This will be equals to 0, and from here this g and g will cancel. We'll get that m1 x1 minus m2 x2 will be equals to 0. Now if you solve it for m2 from here, so m2, this would be equals to m1 x1 over x2. This would be the expression for m2, right? Now suppose if x2 is 2 times x1, if x2 is 2 times x1, so m2 will be half of m1 by using this. So we have obtained that what mass you should place here so that the system is in static equilibrium. Now I'll ask one more question. Now tell me the center of mass of the system. Where is the center of mass for the system? For that we know that xcm, the center of mass, is what we studied in our previous chapters. This would be sigma mx over sigma m, right? This would be equals to. Now here we can take this to be our x equals to 0 point. From here we'll measure the distance. This distance would be negative, so this would be m1 times minus x1, then plus this would be m2 times x2 divided by m1 plus m2. So here I can basically write minus m1 x1, right, like this. Now if I take a minus sign common from here, this would become m1 x1 minus m2 x2 divided by m1 plus m2. This is xcm, right, center of mass for the system. Now from here, from this equation here, m1 x1 minus m2 x2 is 0. So this term, this numerator, this would be 0. And if numerator becomes 0, xcm would be s equals to 0. Where x is 0, we'll get the center. So here where x is 0 at this point where the rod is suspended. So we have observed one thing, what? That the center of mass of a object which is hanged by using any rope or a wire is exactly below the suspended point. Here the center of mass is exactly at this point, and this result is general result. It is not only applicable to two mass system, it is applicable to any system. Confused? Let me take an example so that you have a better understanding. Now consider that a student is constructing a mobile that you can see here that represents some of the major food groups. Right, now their completed artwork is shown in this figure. Now our task is to tell that what should be the mass M1, M2, M3, so that the system is perfectly balanced. So, and we can assume that this string and horizontal roads have negligible mass. Okay. Now, what we can do now, if you apply the zero torque condition, if you apply the zero torque condition for this system, what I can write, you can take this to be your axis of rotation. So M1, let this is 12 centimeter, right? So M1 into 12 minus M2 into 18. This should be equals to 0. Now from here you'll get that M1 is 1.5 times M2, right? Next, you can consider this to be your system, this whole to be your one system. So what I can write? So here we can write that here now the total mass would become M1 plus M2. This is the total mass suspended at here at this point, multiplied with, this is 6 centimeters. So 6 is equals to, or I can write minus 0.30 multiplied with 24 is equals to 0. Or I can write that M1 plus M2 multiplied with 6 is equals to 0.30 times 24. The 6 I can take to the right side, divide by 6, and in place of M1 I can write 1.5 M2, 1.5 M2. From here we can easily find M2. You'll get M2 to be 0.48 kilogram. Put it here, M2 here, you'll get M1 to be equals to 0.72 kilograms. Next, to find M3, how to find this M3? For that you have to consider this whole to be your system. Now this time the mass is on the left side. The mass is on the left side, which is hanged here. This would be 0.20 plus 0.30 plus M1 plus M2. So if I'm just balancing the torque about this point, so what I can write here, that M1 plus M2 plus 0.30 plus 0.20, this is the total mass hanged at this point multiplied with 18. This is the torque minus. One more thing, I'm not considering the acceleration due to gravity g. You may say that you should take m1 g and then 12, but that doesn't matter here because this g and g will cancel. Like the one here we saw that this g and g will cancel, so no need to consider g because this ultimately this will be cancelled. Now minus m3 into 31, and this should be equal to 0. We have m1, we have m2, we just need to find m3. We can easily find from here, you'll get m3 to be equals to 0.99 kilogram. Now did you notice one thing, that if you take this whole to be your system, then the center of mass of this whole system would be exactly at this point where the system is hanged, is suspended by using the string. It is suspended at this point, so this would be the center of mass. Now if you consider only this to be your system, only this to be your system, then where would be the center of mass? If the system is balanced, it is in static equilibrium, so the center of mass for this system would be exactly at this point. So what I want to say is, so whenever an object is suspended by using a string, rope or anything, and it is in static equilibrium, then the center of mass of the object will be exactly below the suspended point. This is what we need to say. Now let's move forward. Now we have one more example for center of mass for suspended object. Now suppose we have this brush hanged about this point. Now center of mass for this brush should be exactly below this point. You may ask why it is exactly below. Because if the center of mass is exactly below, then the torque created by this mg force would be 0, because it is passing through this axis where this object is being hanged. Now suppose you turn this brush to the counterclockwise direction. Now, in this case, the center of mass is shifted. Here, the center of mass is here. Now, because now this would create a torque about the axis of rotation, this torque will create a moment in the clockwise direction and will try to make this brush to rotate in the clockwise direction so that the center of mass is in line with this axis, right? So this is one more example. Now we'll take one conceptual problem. So consider this mallet that you can see here. It is suspended about this point here by using this string and is perfectly balanced in the horizontal position. Now suppose what we do here is we cut the mallet from this exactly from this cross section into two pieces, piece number one, piece number two. We have to tell, is the mass of piece number one greater than the mass of piece number two, or the mass of piece number two is greater than the mass of piece number one, or are they equal? Oh, sorry, this is m, this is one in the same thing. This should be m2 is greater than m1. Is this condition is correct, or this one, or this one? Now you may think, just now we said earlier that m1 x1 minus m2 x2, this should be equals to 0. This is what we have seen. Now if you consider this to be, or this distance, if you take this to be x1, now clearly x1 is less than x2, or x2 is greater than x1. So m1 should be greater than m2. 2 such that m, from this equation what you can write, m1 x1 minus is equals to m2 x2, right? Now this the product of m1 x1 times m2 x2, this product should be equal, otherwise the things will not going to balance. So if x2 is less, sorry, if x2 is more, so x1 will be less. Now to balance this, m1 has to increase and m2 should be less, so that the product is equal. I hope you got the problem what I'm saying. Now as of now we have discussed the center of mass for the object which is hanged. Now what about the objects or system which are standing on, for example, a person standing on two legs, where would be the center of mass? We'll consider a few examples like this now. Now consider this system where the person is standing on two legs. So a system will be in rest as long as the center of mass is vertically above the base on which it is supported. Now here the person is supported by his 2 feet. So the center of mass would be exactly above, approximately in between these two legs, and on this axis it will be at this point. This would be the center of mass in between the two legs. Now suppose what he did is he lift his one leg, this left leg he lifted. Now the center of mass has to be above this foot, otherwise he will not able to stand, he will fall. So to adjust his center of mass, because earlier the center of mass was here, now because now he's standing on one leg, so center of mass should be shifted to this side. So what he did is he changed his posture to this side, the left side, and to balance it, he has to open his this second leg to the right side, so that the center of mass is somewhere above this foot, approximately at this point. Then only he'll able to balance his body, otherwise he'll not be able to balance, he'll going to fall. Now this experiment you can try at your home also. Try to stand on one leg without changing the posture. You'll definitely going to fall. You have to change the posture of your body, otherwise you're going to fall. Okay, now let's move on. Now see, this woman may not have the idea of center of mass, but she exactly know from her previous experiences that how to balance her body on one leg while cleaning the window. She leans her body forward and one leg backward so that the center of mass for her body is exactly above the point, above the foot on which she is standing. If the center of mass is not above this foot, she will going to fall. No doubt about this. Let's take a couple of more examples. Now see this. This rock is in one of the national park in USA. Now the rock might be standing for the thousands of years and it's not falling. Why? Because the center of mass is exactly above the base of its support. Because center of mass lies above its base of support. This is the base. Center of mass will lie exactly above this. That is why it's not falling. Now kangaroos. Here also we can understand the center of mass. Now kangaroo has a long tail. It has a long tail which helps it to maintain its balance both on the solid ground and in flight between hops. So here the center of mass would be when the body lands, the center of mass would be exactly above the base of support, somewhat here. And when it is in motion, then also the center of mass would be at this position. And because of this long tail helps the kangaroo so that the center of mass is above the base of support. This is also we can understand from the body of kangaroo. Now this is all with this topic. Next we'll start the dynamic application of torque in this video itself. Now we're going to see dynamic application of torque, and under this topic we'll explore how we apply Newton's second law in a rotational motion. We have seen earlier how to apply the Newton's second law in linear motion, but now we'll see in rotational motion. So consider this figure. Here we have this this pulley of mass m, radius r, and the string is wrapped around the pulley. On the other side we have this block with mass m. Now when the mass is released, this block is released, it accelerates downwards, and the string, suppose string unwraps without slipping and the pulley rotates without friction. Now then in that case, what would be the acceleration A? You may think that acceleration A would be equals to acceleration due to gravity, but this will not be the case here. Why? Now because this pulley is not massless, so the pulley will going to resist any rotation, and for the pulley to have rotation we have to apply torque, which in this case will apply this tension force T. This tension force T will be a tangential force to the pulley, and due to this tangential force the torque will be applied and the pulley will go to rotate. And the same tension force would be acting in the upward direction here on the mass side, this block side. If you see the free body diagram, this is the block of mass m. Gravity force would be acting in the downward direction and this tension force would be acting in the upward direction. So clearly acceleration A is not equals to g, it will be less than g. So this was the basic idea. Now let's try to apply the Newton's second law for this on the pulley and also on this mass m separately. Now before applying the Newton's second law, we have to define the direction, at which direction is positive, which direction will be taken negative. Now when the block moves upwards, the pulley will rotate counterclockwise. So upward direction will be taking positive, so this counterclockwise direction will also be positive, right? So this was the direction we have taken. Now if you consider this is a pulley here, it in this case it is moving, it is rotating in the clockwise direction like this, and here we have this tension force T, right? And if you see the block of mass m, here we have this upward direction T, and the gravity force would be acting in the downward direction, right? Now let's first apply, and this is acceleration A. Now let's first apply the Newton's second law for this linear motion. Here is the linear motion for the this block of mass m. So I can write upward direction we have taken positive, so T minus mg, this would be equals to mass times acceleration, right? Now if you apply the Newton's second law of motion here, I can write that net torque is equals to, net torque we represent it with tau, so net torque acting on the system is equals to I into alpha. I into alpha. Here we have only the torque due to this tension force T, and it is making out clockwise torque, so we have to take negative, so minus T into R, because this direction we have taken positive, is equals to I into alpha, right? And because the this string unwraps without slipping, so for this condition only we can write that acceleration will be equals to R into alpha, and from here alpha would be equals to A over R. We can replace it here, I times this is A over R. Either you can write small r or capital R, so I'm writing small r because we have taken capital R, so I'm writing capital R only. So here also I should write capital R, right? This is minus T into R, and from here what we can write, that T will be equals to minus I A over R square, right? Now we have one tension from here. If you see, this tension T would be equals to MA plus mg. So we can replace this T here and we can find acceleration. So what I can write, that MA plus mg is equals to minus IA over R square. Now further divide with m both the side, so here also divide with m, here also. So this would become A plus G is equals to minus I A over mr square. Now take this term to the left side and this G to the right side. I'm writing it here. So A plus IA over mr square is equals to minus G. Take A common, so 1 plus I over mr square is equals to minus G, and from here acceleration A, this expression we obtained as minus G over 1 plus I over mr square. And from this formula we can say, we can conclude many, we can observe many things. First thing is that this acceleration A comes out to be as negative. That means the object is accelerating in the downward direction, because downward direction is negative and upward direction we have taken positive. That is clear. Next, acceleration A is less than 0. Why? Because this denominator is greater than 1, so acceleration A will be less than G. Next, if you consider that now if you take mass of the block to be very much greater than the mass of the pulley, then in that case acceleration A will be approximately equals to G value, if you see just the magnitude. Or if I is 0, if the moment of inertia for the pulley is 0, then in that case also A will be equals to minus G, because if I is 0, this term goes to 0. If this is 0, 1 plus 0 is 0, sorry, 1 plus 0 is 1, so you'll get A to be equals to minus G. Next thing we can take, if I becomes very much huge, if I becomes infinite, then acceleration will goes to 0. Because if this is infinite, so 1 plus infinite is infinite and 1 over infinite is 0. So acceleration will be 0. Acceleration for the block, that means the block will not going to move. In real sense, think in that manner. If the moment of inertia is huge for this pulley, this moment of inertia is huge, so it will resist the rotation in with very much high magnitude. Then due to this, the pulley will not going to rotate. So if pulley does not rotate, so mass will not accelerate, and thus the acceleration will be zero. This is what we have seen here, right? Now we'll consider one example to understand it better. Now here we have this, we are given with this figure. Here you can see we have this cart of mass 0.31 kilogram, and this cart is attached to this string. Now string passes over a disc-shaped pulley, and the mass of this pulley we have 0.080 kilogram, and the radius r is given to be 0.012 meter. Now this string is pulled vertically downward with a constant force of F to be 1.1 Newton. Now two things you have to find. First, the tension in the string between the pulley and the cart. That means that what would be the tension here? This tension T is what we need to find. And the acceleration of the cart. What would be the acceleration? So these two things we have to find. So we have to apply the Newton's second law. Here the motion for the cart would be linear motion. So here we're going to apply the Newton's second law for the linear motion. And here we have to apply the Newton's second law for a rotational motion. Now when the cart accelerates in this direction, the pulley rotates in counterclockwise direction. So this direction will be taking positive. So this direction would be positive for the cart, for the pulley, right? Now if I sketch it here, this is the pulley here, this is the tension T, this is the force F, which is given to be 1.1 Newton, right? Now this tension T will create a clockwise torque, and this force F is creating anti-clockwise torque. So by using the Newton's second law, I can write that the net torque on the system is equals to I into alpha. So net torque we have, this is minus T into R, and this would be plus F into R. This would be I into alpha. I is, here this pulley is a disc-shaped pulley of mass M, and radius R is given to be 0.02. So 1 by 2 mr square, this would be the moment of inertia multiplied with alpha. Now because this string unwraps without slipping and the friction is not present here, so alpha can be written as A over R, right? Now this R and R will cancel, and also if you take R common here, this should be small r, not the capital one. If I take R common, so this R and this R will also cancel. So what we are left with, F minus T is equals to M times A divided by 2. Okay, now if you consider this cart, and this is the positive direction we have taken, and here we have only this tension force T. So this T would be equals to, let this be capital M, so the mass be capital M, so mass times acceleration by using the Newton's second law of motion. So from here acceleration A would be T over M, so I can replace it here. So F minus T is equals to M times A, we have T over capital M, and this is divided by 2. Now can you solve it for T from here? Of course we can. We can take this T to the right side. This would become plus T. Now if I take T common from here, so we are left with this thing, and from here this tension force T would be equals to F over 1 plus M over 2 times capital M. What is M? This small m is the mass of this pulley, and capital M is the mass of the cart. Now it's pretty simple, just plug the values. F is given to be 1.1, 1 plus small m we have 0.08 divided by 2 times capital M we have 0.31 kilogram. Solve this, you'll get the result to be 0.97 Newton. So the tension force T is less than the force applied. This tension T is less than the force applied, and that is why the pulley is rotating in the counterclockwise direction, because this F is greater, so torque will also be greater due to this force F. Radius means the same for both the torque. Okay, now L, this acceleration A would be T over M. This thing we have written earlier. Tension we have 0.97. Mass of the cart is what? 0.31. That would be 3.1 meter per second square. This would be the acceleration A. Right? And here we observe one case that if the mass of the pulley is 0, and in general in some cases we don't take the mass of the pulley. In that case, this force applied would be equals to the tension T, and acceleration A would be equals to F over M. But because the mass of the pulley is not negligible, so it will resist any rotation, and due to this the acceleration will be less, which is equals to this. Right? Now I'm giving one question to you. What is the force, what applied force is necessary to give a cart an acceleration of 2.2? So what force you should apply on the pulley to give a cart an acceleration of 2.2 is what you have to tell. Also one more thing. Now when we started with the topic dynamic application of torque, I discussed this case. Now you have to tell that if you see the free body diagram for this block M, here this we have the gravity force mg, this is the tension force T. Which force is greater? Is T is greater than mg, or mg is greater than T? You have to tell. Many of you might say that we discussed this equation that T minus mg is equals to mass times acceleration, so T is equals to mg plus ma, so T will be greater than mg. No, that will not go into the case. Don't always use formulas. Here the object is moving, this cart is accelerating in the downward direction. This force has to be more, then only the cart can move downwards. Otherwise how can it move downwards if this tension force is greater? This would be the correct. Okay, now this is all with this video. If you have any confusion regarding to anything in this video, you can comment me in the comment box below. I'll definitely going to rectify it. But for now, we're going to finish this video. I will meet you in the next video where we discuss one more important topic, which is angular momentum. So, and also we'll see the conservation of angular momentum. So with this, I'm going to end this video. Goodbye.